The overall goal of this procedure is to quantify the change in stiffness on a polyvinyl acetate-based nanocomposite structure as a function of time implanted in tissue. This is accomplished by first patterning the polymer nanocomposite samples and adhering them to acrylic holders for insertion into tissue and micromechanical testing. The second step is to prepare a microtensile tester environment to mimic the physiological environment ex vivo using a humidity source and a radiant heat source. Next, the implant sample is inserted into tissue and removed after a specified duration. The final step is to load the sample into the environmentally controlled microtensile tester and perform the mechanical testing to determine the Young's modulus of the material after the specified implant duration. Ultimately, this environmentally controlled microtensile testing is used to show the changes in mechanical stiffness as measured by Young's modulus as a function of time exposed to the physiological environment.
The main advantage of this technique over existing methods of measuring variable mechanical properties, like dynamic mechanical analysis, is that it can be applied to microscale samples, and the humidity and temperature can be controlled.
This method can help answer key questions in the neural interfacing field, such as how the inflammatory response to an implant is affected by the stiffness of the implant material.
First, obtain polyvinyl acetate-based nanocomposite film with a thickness of 25 to 100 micrometers, produced with the solution casting and compression technique. Next, adhere the film to a silicon wafer by heating on a hot plate at 70 degrees centigrade for 2 minutes.